In this video, we're going to continue our discussion of electrophilic aromatic substitution. In the last video, we looked at the examples of halogenation with bromine and chlorine. In this video, we're going to study two more types of EAS, and that is sulfonation and nitration. So, in sulfonation, we're adding SO3H to our benzene ring. And the reagent we use for that is called fuming sulfuric acid. And fuming sulfuric acid is a mixture of sulfuric acid and sulfur trioxide gas. The reason they call it fuming is because this stuff both looks and is nasty. When you take the lid off it, you can see the sulfur trioxide fuming out of the bottle, and it's incredibly corrosive. So one of the keys to all of these electrophilic aromatic substitution reactions is that because benzene is so unreactive, we need powerful electrophiles, and sulfur trioxide fits that bill. There are a couple ways that we can sort of understand its electrophilicity. One explanation relies on the fact that the size of the 3p orbital in sulfur is very different than the 2p orbital on oxygen. And so we get very inefficient overlap. And it turns out the charge is localized on the oxygen atom. Because that 2p orbital is smaller, the electrons can get closer to the oxygen nucleus, and that makes them happier. As a result, the SO bond has significant single bond character, where it's largely a single bond and those pi electrons are localized on the oxygen atom. So you end up with a positive sulfur and a negative oxygen. By the time you attach 3 oxygens to that sulfur atom, the effect is compounded. Another way we can rationalize this is by thinking about the resonance structures that we can draw. One of the patterns of resonance structures that we learned is when we have 2 atoms of different electronegativities connected by a pi bond, we can draw this resonance structure. Right, and then we can do this for all of the oxygen atoms and even combinations of multiple oxygen atoms with the sulfur. And so, based either on sort of molecular orbital thinking or based on the resonance structure we can draw, I think both cases would show us that this sulfur has a very large partial positive charge, and so it's going to be a very strong electrophile. All right, now the sulfonation mechanism is very similar to the mechanisms that we saw with bromine and chlorine in the last video. The one big difference is that there is an extra proton transfer step. In all of these mechanisms, we started out with a nucleophilic attack. Pi bond on the benzene ring attacks our electrophile. This generates the sigma complex with a positive charge on the benzene ring. Whenever you're asked to draw these mechanisms, be sure you show the 3 resonance structures stabilizing this sigma complex. We then have a proton transfer, and in this case, water is acting as the thing that's stealing the proton. And then the other difference is we have this additional proton transfer step that we didn't have when we added bromine and chlorine. The big difference being when we added bromine and chlorine, essentially we were adding Br plus and Cl plus. So we're adding something positive. In the end, we ended up with a neutral after the first proton transfer. In this case, because we're adding something neutral to start with, right, the charges are off by 1. And so we need this second proton transfer in order to give us the final product. Now we're going to talk more about these reactions as the chapter goes on. One important thing that we want to remember is this sulfonation process is very sensitive to the concentrations, and it's actually a reversible process. So in concentrated fuming sulfuric acid, we're going to cause the sulfonation of benzene to occur. If instead we use dilute sulfuric acid, we can remove this SO3H group. And so it turns out this is going to be really important when we talk more about synthesis later in the chapter. So we want to be sure that we remember that this reaction is reversible. Okay, moving on to another type of electrophilic aromatic substitution, and that is nitration. In this case, we're going to react our benzene with a mixture of nitric acid and sulfuric acid. It turns out the electrophile in this reaction is the nitronium ion, or NO2+. So let's see how we make the nitronium ion from our combination of nitric acid and sulfuric acid. To make the nitronium ion, we're actually going to have a reaction, an acid-base reaction, between nitric acid and sulfuric acid, in which sulfuric acid acts as the acid and nitric acid acts as the base. Now, it may seem weird at first for nitric acid, which we know is a very strong acid, to be acting as a base, but strong acid is all relative. Turns out sulfuric acid is significantly stronger by a couple orders of magnitude than nitric acid. So in this mixture, we will get this acid-base reaction. That gives us this protonated nitric acid. We essentially have a water here, and so when that water pops off, that gives us the nitronium ion. And this is our active electrophile for the electrophilic aromatic substitution. And it probably makes sense that this is electrophilic, right? Nitrogen with a positive charge. We have a pretty electronegative element with a positive charge, and so it's not happy. It's looking for electrons. All right, now this mechanism is hopefully going to start to look familiar. We have a nucleophilic attack to make the sigma complex, and then we end it off with a proton transfer. And like the first mechanisms we saw when we were adding Br plus and Cl plus, we end up with a neutral compound after the first proton transfer, so we only need the one proton transfer as opposed to the two that we needed with the sulfonation. All right, this last slide is another note on useful synthesis reactions. So a nitro group, it turns out, can be reduced into an amine by reacting it with either iron or zinc in the presence of HCl, and then in a second step adding sodium hydroxide. So if we start with a benzene ring and we want to make an amine as opposed to a nitro group, we'll just go through the nitro group as an intermediate. So first we'll react it with our mixture of nitric acid and sulfuric acid. This will give us the nitro group added to the benzene. Then if we react the resulting nitro group with iron or zinc in the presence of HCl, then hit it with sodium hydroxide, that will give us our amine added to the benzene.